Look up at the night sky tonight, and you'll see countless stars shimmering like eternal beacons. But what if I told you that one of those distant lights could be on the verge of a violent, spectacular end, and that its death might hold the key to Earth's own forgotten future? Stars don't live forever, and when they die, they don't just vanish quietly. They explode, collapse, or fade in ways that rewrite the rules of the cosmos. And hidden within those final moments are clues, echoes of what might one day happen to our own planet. This isn't just about distant celestial events, it's about us. Because the fate of stars and the fate of worlds are more connected than you might think, take a moment to picture a star like our Sun, but older, exhausted, its fuel running out. In its final act, it doesn't go gently. It might swell into a red giant swallowing planets whole, or collapse into a dense white dwarf, its core left glowing like a cosmic ember. These aren't just dramatic space phenomena, they're glimpses into Earth's own distant timeline, because stars, in their death throes, leave behind a kind of cosmic blueprint. The elements they scatter across the universe become the building blocks of new worlds, new life, and the forces that shape their endings. Those same forces will one day shape ours. So what does a dying star teach us about Earth's future? The answers are written in stardust and gravity, in the way celestial bodies live, die, and transform. Over the next few minutes, we'll unravel how the violent end of a star millions of light years away mirrors the slow, inevitable changes awaiting our own planet. We'll explore how scientists decode these cosmic messages and why understanding stellar death isn't just about astronomy. It's about preparing for the unimaginably distant, yet very real future of our home. This journey will take us from the heart of collapsing stars to the fragile balance that keeps Earth alive, and by the end, you'll never look at the night sky the same way again. Every star in the night sky is born from the same cosmic recipe, a swirling cloud of gas and dust, collapsing under its own gravity until the pressure at its core ignites the fires of nuclear fusion. This moment marks the beginning of a journey that can last billions of years, a journey that will end in ways as varied as the stars themselves. The smallest stars, called red dwarfs, burn their fuel so slowly they could outlive the universe as we know it, fading gently into darkness like embers cooling in a cosmic hearth. But the fate of larger stars like our Sun is far more dramatic. After billions of years of steady burning, they swell into red giants, their outer layers expanding until they engulf nearby planets. Then they shed those layers in a glowing planetary nebula, leaving behind a dense, Earth-sized core called a white dwarf, a stellar remnant that will slowly cool over trillions of years. Yet the most massive stars don't even get that quiet ending. When they run out of fuel, their cores collapse in an instant, triggering a supernova explosion so powerful it can outshine an entire galaxy. In that blinding flash, elements like gold, platinum, and uranium are forged in the heart of the explosion, then scattered across space. These are the same elements that make up our planet, our oceans, even our bodies. Every atom of oxygen in your lungs, every speck of iron in your blood, was once part of a dying star. That's the incredible truth. We are literally made of stardust, the remnants of celestial giants that lived and died long before Earth existed. But why does this matter for our planet's future? Because the same forces that govern a star's life cycle also shape the destiny of worlds. When our Sun eventually becomes a red giant, its expanding outer layers will vaporize Mercury and Venus and likely engulf Earth. Even if our planet survives, it will be a scorched, lifeless rock, and long after the sun shrinks into a white dwarf, the universe will keep evolving. Galaxies will drift apart, stars will burn out, and the cosmos will grow colder and darker. Earth's fate is written in the life cycles of stars, not as a prophecy of doom, but as a reminder of the breathtaking scale of time and change. The death of a star isn't an ending. It's a transformation, a recycling of matter and energy that fuels new beginnings. And somewhere, billions of years from now, the atoms that once made up our world may find themselves part of something new, another star, another planet, perhaps even another story. The fate of a star isn't just about how it burns, it's about how much it weighs. That invisible number, its mass, holds the secret to its final act. For stars like our Sun, the ending is almost poetic. After billions of years of steady light, it will swell into a red giant, its outer layers puffing outward like a cosmic sigh. Those layers will drift away, forming a glowing shell of gas called a planetary nebula, though ironically, it has nothing to do with planets. At the center, the Sun's core will remain, compressed into a white-hot ember no larger than Earth. This white dwarf will glow faintly for trillions of years, a quiet monument to what once was. But the universe has far more dramatic exits in store for heavier stars. Imagine a star 10 times more massive than our Sun. When its fuel runs out, gravity doesn't gently reshape it, it crushes it in an instant. The core collapses at nearly a quarter the speed of light, then rebounds in a cataclysmic supernova explosion. For weeks, this single star can outshine its entire galaxy, scattering newly forged elements across space. What remains is even more extraordinary. If the core is between 1 and 3 times the Sun's mass, it becomes a neutron star. A teaspoon of its material would weigh 1 billion tons on Earth. And if it's heavier still, the collapse doesn't stop until it forms a black hole, where gravity is so strong not even light can escape. These stellar deaths aren't just spectacular light shows, they're cosmic factories. The incredible heat and pressure inside a dying star create elements far heavier than the hydrogen and helium it was born with. Gold in your jewelry, the uranium that powers nuclear plants, even the calcium in your bones, all were forged in these violent final moments. Without supernova, Earth would be missing the very ingredients that make life possible. And here's where the story loops back to us. In about 5 billion years, our Sun will begin its own transformation into a red giant. Earth may escape being swallowed whole, but the oceans will boil away, the atmosphere will vanish, and the surface will become molten rock. Yet even this isn't the true end. The white dwarf left behind will still hold most of the Sun's original mass, its gravity subtly tugging at the ruins of our solar system. Over incomprehensible stretches of time, that remnant will cool until it's no longer a glowing ember but a black diamond in the dark, a cold, dense relic of the star that once nurtured life on Earth. This cosmic perspective changes everything. The same processes that end stars also create the conditions for new beginnings. Every planet, every living thing, carries the fingerprints of stellar deaths that happened long ago. When we look up at the night sky, we're not just seeing distant lights, we're seeing the past, present, and future of our own world written in starlight. The universe recycles itself in the most extraordinary ways, and Earth's story is just one paragraph in that endless epic. 5 billion years might sound like an unimaginable stretch of time, longer than all of human history multiplied by 1,000,000. But in the life cycle of a star, it's just a blink. Right now, our Sun is middle-aged, steadily fusing hydrogen into helium at its core. But this stable phase won't last forever. Every second, the Sun consumes 600 million tons of hydrogen, and as that fuel dwindles, the clock ticks closer to a transformation that will reshape our solar system entirely. When the Sun's core finally runs low on hydrogen, the balance between gravity and nuclear fusion will tip. Gravity will compress the core, heating it until it can fuse helium into heavier elements, while the outer layers expand outward, cooling into a reddish hue. This is the red giant phase, a swollen, luminous version of the star we know today. The Sun's surface will stretch beyond the orbit of Mercury, then Venus, and possibly even Earth. Even if our planet isn't swallowed whole, the heat will strip away the atmosphere, boil the oceans, and turn the surface into a molten wasteland. The very rocks will vaporize. Yet this isn't just a story of destruction. The Sun's death throes will also seed the cosmos with new possibilities. As it sheds its outer layers, those gases will enrich interstellar space with carbon, nitrogen, and oxygen elements forged in its core. These are the raw materials for future stars, planets, and perhaps even life elsewhere. The Sun's demise, in a way, becomes a cosmic recycling program. And here's the profound twist: this process isn't unique. Across the galaxy, countless stars have already undergone this transformation, their remnants now drifting as white dwarfs or scattered nebulae. By studying them, astronomers can read the solar system's future like a blueprint. Take the ghostly ring of the Helix Nebula, for example, a preview of what our Sun might look like in its final stages. At its center, a white dwarf glows with residual heat, while the surrounding gas tells the story of its violent rebirth. So what does this mean for Earth? It's a humbling reminder that permanence is an illusion. The same forces that gave us life, the Sun's light, the Earth's orbit, the delicate balance of chemistry, will one day undo it all. But there's also a strange comfort in this cosmic perspective. The elements that make up our world, and even our bodies, were born in stars that died long ago. And when our Sun fades, its remnants will become part of something new. The universe doesn't end, it reinvents itself. This isn't just about accepting an inevitable fate. It's about understanding our place in a grand, ever-changing cycle. The Sun's death won't just erase Earth's history, it will add to a much larger story, one written in stardust and gravity. And long after our planet is gone, those atoms might find themselves part of another world, another sun, another chance for life to begin again. Supernova are the universe's ultimate paradox, catastrophes that create, infernos that forge. When a massive star reaches the end of its life, it doesn't fade quietly. Instead, its core collapses in less than a second, rebounding with an explosion so powerful it can outshine entire galaxies for weeks. This is nature's most extreme alchemy. The temperatures and pressures inside a supernova are so intense that atoms are smashed together, forming elements far heavier than anything a star could make during its normal life. Gold, platinum, uranium, these rare metals aren't just lying around in space. They're born in the heart of stellar explosions, then blasted outward at nearly the speed of light. But supernova aren't just element factories, they're also cosmic wrecking balls. Any planet orbiting too close would be vaporized in an instant, its atmosphere torn away by the sheer force of the blast. Even from thousands of light years away, a nearby supernova could bathe a world in deadly radiation, stripping away its protective layers and leaving it exposed. It's a terrifying thought, but also a necessary one, because without these violent deaths, life as we know it wouldn't exist. Take the Crab Nebula, the remnants of a supernova observed on Earth in the year 1054. At its center spins a neutron star, a city-sized object so dense a single teaspoon of it would weigh 1 billion tons. Around it, filaments of gas stretch outward, still expanding almost 1,000 years later. This debris is laced with oxygen, carbon, and iron elements that will eventually mix with interstellar gas, becoming part of new stars and planets. The same explosion that destroyed a star also planted the seeds for future worlds. This duality is written into the fabric of the cosmos. Destruction and creation aren't opposites, they're part of the same cycle. The calcium in your bones, the iron in your blood, even the iodine that regulates your metabolism, all were forged in the fury of dying stars. Supernova are the reason Earth has mountains, oceans, and life at all. They're also a stark reminder that nothing lasts forever. One day, long after our sun has faded, another star in our galactic neighborhood will explode, scattering its enriched remains into the void. Those atoms might one day become part of a new planet, orbiting a new star, nurturing new life. Studying supernova isn't just about understanding the deaths of stars, it's about tracing the journey of the very stuff we're made of. Every time we look at the Crab Nebula or other supernova remnants, we're seeing a preview of what could happen to our own solar system, billions of years from now. But more than that, we're glimpsing the universe's endless capacity for reinvention. Stars die, but their remains become the building blocks of the future. In that sense, we're all just temporary arrangements of stardust, waiting to return to the cosmic cycle that made us. White dwarfs are the universe's quietest storytellers, glowing faintly with the memories of stars long gone. Picture a sphere no bigger than Earth, yet holding half the mass of our sun. A teaspoon of its material would weigh as much as an elephant. These stellar remnants are what stars like ours become after they've exhausted their nuclear fuel and shed their outer layers into space. But they're far from lifeless. A white dwarf starts out scorching hot, with surface temperatures reaching over 100,000 degrees, nearly 20 times hotter than the sun is today. Over time, that heat slowly leaks away, and the white dwarf cools, fading like a dying ember in a cosmic fireplace. What makes white dwarfs so fascinating isn't just their extreme density or gradual dimming, it's what they reveal about the past. Because heavier elements sink to their cores, the outer layers of a white dwarf act like a pristine snapshot of the star's final chemical makeup. Astronomers can analyze the light from these cooling cinders to uncover what elements were present when the star died. Some white dwarfs even show traces of planetary debris in their atmospheres, the last remnants of worlds that once orbited them. Imagine finding the ghostly fingerprints of shattered planets, proof that entire solar systems met their end long ago. Our own sun will one day join this cosmic graveyard. In about 5 billion years, after swelling into a red giant and casting off its outer layers, it will leave behind a white dwarf that will glow for trillions of years before fading entirely. The planets that survive the sun's expansion, if any remain, will orbit this dense relic in darkness, their surfaces frozen under a dimming pinpoint of light. But even in death, the sun's white dwarf phase will shape its surroundings. Its intense gravity could perturb asteroids or comets, sending them spiraling inward in a final dance of destruction. And here's the remarkable part: white dwarfs don't just tell us about the future of our solar system, they help us measure the age of the universe itself. Because they cool at predictable rates, the faintest white dwarfs we observe serve as cosmic clocks, confirming that the universe is roughly 13.8 billion years old. The oldest white dwarfs are like celestial fossils, remnants of some of the first stars that ever shone. By studying them, we're peering back into the universe's earliest chapters while simultaneously glimpsing Earth's distant fate. Yet even white dwarfs aren't truly eternal. Given enough time, far longer than the current age of the universe, they will cool completely, becoming black dwarfs, cold, dark spheres of crystallized carbon and oxygen drifting silently through space. No black dwarfs exist yet. The universe simply hasn't been around long enough for any white dwarf to reach that final state. But one day, trillions of years in the future, the last white dwarf will fade, marking the end of the stellar era. Until then, these stellar ghosts continue their slow, silent vigil, carrying the echoes of dead stars into the far future. Neutron stars are nature's most extreme physics experiments, cosmic laboratories where matter gets pushed beyond anything we can recreate on Earth. Imagine taking the entire mass of our Sun and crushing it into a sphere no wider than Manhattan. The result is so dense that a single sugar cube of its material would weigh as much as Mount Everest. But the real magic happens when these collapsed stars start spinning. Some rotate hundreds of times per second, sending out beams of radiation that sweep across space like lighthouse beacons. When those beams cross Earth's path, we detect them as rapid pulses of light, earning these objects their name, pulsars. The first pulsar discovered, back in 1967, baffled astronomers with its perfectly timed radio blips. So precise were these pulses that scientists initially nicknamed the source LGM-1, short for Little Green Men, before realizing they'd found a natural cosmic clock more accurate than any atomic timekeeper on Earth. Today, we know pulsars as the spinning remnants of massive stars that went supernova. Their extreme gravity locks their rotation into near-perfect consistency, with some slowing by just 1 second every few million years. This incredible stability makes them ideal tools for testing Einstein's theory of relativity. When astronomers observe how pulsar signals bend around other massive objects, they're essentially using these cosmic lighthouses to map the warping of spacetime itself. But neutron stars aren't just precise, they are also laboratories for the bizarre. Under their incomprehensible gravity, atoms get crushed so tightly that electrons merge with protons, turning the entire star into a giant nucleus of pure neutrons. Some develop crusts 100 billion times stronger than steel, while their interiors may contain exotic states of matter we've never seen, like nuclear pasta, where particles arrange themselves into shapes resembling spaghetti or lasagna sheets under the extreme pressure. There's even evidence that the cores of the most massive neutron stars might collapse further, becoming quark stars where individual particles break down into their fundamental components. Perhaps most astonishing are magnetars, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. These cosmic powerhouses can unleash starquakes that ripple across their surfaces, releasing bursts of gamma rays powerful enough to affect Earth's upper atmosphere from halfway across the galaxy. In 2004, a magnetar 50,000 light-years away emitted a flare so intense it temporarily ionized our planet's ionosphere, even though the explosion occurred before human civilization existed. Events like these remind us that neutron stars aren't just distant curiosities. Their extreme physics can reach across interstellar space to touch our world. What does this mean for Earth's future? While our solar system likely won't form a neutron star, our sun isn't massive enough. These objects show us how matter behaves when pushed to its limits. The same quantum forces that govern a pulsar's spin also shape the electrons in our devices. The nuclear reactions that power supernova are just extreme versions of processes we harness in medical imaging. By studying these stellar remnants, we're not just learning about the deaths of stars, we're uncovering fundamental truths about the fabric of reality that affect everything from the smallest particles to the fate of galaxies. And there's something poetic about that. These ultra-dense stellar corpses, born from violence and chaos, become our most precise cosmic timekeepers. Their radiation beams cut through the darkness like searchlights, illuminating secrets about gravity, matter, and time itself. Long after the stars that birthed them have faded from view, neutron stars continue spinning, pulsing, and teaching us, proving that even in death, stars have more to say. Black holes represent the universe's most dramatic final act, a point of no return where the normal rules of physics break down. When the most massive stars exhaust their fuel, their cores collapse with such force that not even the pressure of neutrons can stop it. The star's entire mass crushes inward until it forms a singularity, an infinitely dense point wrapped in an invisible boundary called the event horizon. Cross that threshold and there's no coming back. Not even light can escape the gravitational grip, rendering black holes invisible to direct observation. Yet their presence is betrayed by the chaos they create. Gas and dust spiral inward at nearly the speed of light, heating up to millions of degrees and glowing brightly before vanishing forever. But black holes aren't just cosmic vacuum cleaners. They are also time capsules, preserving information about the stars that birthed them. The mass and spin of a black hole carry echoes of its progenitor's final moments, like a fingerprint etched into spacetime itself. Take Cygnus X1, the first black hole ever confirmed. Its 21 solar masses suggest it was born from a colossal star that lived fast and died young, leaving behind a gravitational monster orbiting a blue supergiant companion. The two dance a deadly waltz, with the black hole slowly stripping material from its neighbor, creating an accretion disk so hot it emits X-rays detectable across the galaxy. What makes black holes truly fascinating is how they warp reality. Near the event horizon, time slows to a crawl due to extreme gravity, a phenomenon called time dilation. An observer watching from afar would see a falling object appear to freeze at the horizon, its light redshifted into invisibility, while someone crossing it would experience no such delay. This paradox hints at the strange interplay between gravity and quantum mechanics, a frontier physicists are still struggling to reconcile. For Earth, the good news is our sun lacks the mass to become a black hole. But studying these objects teaches us about the universe's most extreme environments. Supermassive black holes, millions to billions times heavier than our sun, lurk at the centers of galaxies, including our own Milky Way. Their gravity shapes entire galaxies, influencing star formation and cosmic evolution. Even more mind-bending are theoretical primordial black holes, possibly formed in the universe's first second, which could be as small as an atom yet as massive as a mountain. Perhaps the most profound lesson black holes offer is about entropy, the universe's tendency toward disorder. When matter falls into a black hole, it effectively disappears from our observable universe, taking its information with it. This information paradox challenges our understanding of quantum mechanics, suggesting black holes might not be the ultimate endpoints we once thought. New theories propose that information could be encoded on the event horizon's surface, projected like a hologram, a clue that even in the darkest corners of space, the universe keeps meticulous records. So while Earth will never face a black hole's oblivion, these enigmatic objects force us to confront the limits of our knowledge. They're reminders that the cosmos operates on scales and rules far beyond everyday experience, where time bends, space twists, and matter vanishes into the unknown. Yet through them, we glimpse the universe's capacity for reinvention, proving that even in destruction, there are mysteries waiting to be unraveled. Planetary nebulae are the universe's most stunning farewell letters, vibrant, glowing signatures written by dying stars. Imagine a star like our sun, reaching the end of its life after billions of years of steady burning. As its fuel dwindles, it doesn't just flicker out. Instead, it swells into a red giant, then sheds its outer layers in a series of gentle, shimmering waves. These expelled gases, lit up by the star's still hot core, form intricate, luminous structures that linger for a cosmic blink just tens of thousands of years before fading into the darkness. That's the paradox of planetary nebulae. They're both a star's final breath and its most dazzling display. Take the Ring Nebula, for example. From our vantage point, it looks like a perfect smoke ring suspended in space, its delicate blues and greens tracing the glow of ionized oxygen and hydrogen. But this isn't just a static shell, it's a dynamic, expanding bubble, hurtling outward at speeds of tens of kilometers per second. The central star, now a white dwarf, bathes these gases in ultraviolet light, making them fluoresce like a cosmic neon sign. And here's the twist: despite their name, planetary nebulae have nothing to do with planets. Early astronomers called them that because their round shapes resembled the fuzzy disks of distant worlds through primitive telescopes. The misnomer stuck, a reminder of how our understanding of the cosmos evolves. What makes these nebulae so scientifically precious isn't just their beauty, it's their role as cosmic recyclers. The gases they eject are rich in carbon, nitrogen, and other elements forged during the star's life. These materials drift into interstellar space, eventually mixing with giant molecular clouds that will collapse to form new stars, planets, and perhaps even life. Every carbon atom in your body, every nitrogen molecule in Earth's atmosphere, likely passed through a planetary nebula at some point in its history. The death of one star becomes the raw material for another's birth, a celestial circle of life written across light years. Yet for all their significance, planetary nebulae are fleeting. Their delicate structures dissipate so quickly on cosmic timescales that catching one in its full glory is like stumbling upon a soap bubble mid-pop. Some, like the Helix Nebula, reveal intricate patterns, spiral tendrils, or comet-shaped knots carved by the dying star's magnetic fields or the gravitational tug of unseen companions. Others, like the Butterfly Nebula, stretch into vast, symmetrical wings, shaped by jets of material screaming outward at hundreds of kilometers per second. Each one is unique, a fingerprint of stellar physics and chemistry playing out in real time. Our own sun will join this stellar gallery one day. In about 5 billion years, it too will puff away its outer layers, creating a planetary nebula visible from distant star systems. The spectacle won't last long, perhaps 30,000 years, but for that brief window, our solar system will glow like a cosmic lantern, its light a final testament to the star that nurtured life on Earth. And just as ancient stars seeded our planet with the elements for life, the sun's remnants will someday enrich future worlds we'll never see. That's the quiet poetry of planetary nebulae. They remind us that even in death, stars don't vanish, they transform, scattering the ingredients for new beginnings across the cosmos. The next time you gaze at images of these glowing shells, remember, you're not just looking at a dying star. You're seeing the universe's way of turning endings into art and ensuring nothing, not even stardust, ever truly goes to waste. Stellar winds are the quiet architects of the cosmos, invisible rivers of particles that flow from stars like our sun, carrying away tiny fragments of their mass with every passing second. These outflows might seem insignificant compared to the explosive drama of supernova or the dazzling glow of planetary nebulae, but their cumulative effect is staggering. Over millions of years, even a modest star's wind can strip away enough material to reshape entire planetary systems, dispersing elements forged in its core into the void. Consider our own sun. Its solar wind, a stream of charged protons and electrons, blows outward at nearly 1,000,000 miles per hour, creating a protective bubble called the heliosphere that shields our solar system from harsh interstellar radiation. But this wind isn't constant. During periods of heightened activity, like solar flares or coronal mass ejections, the sun can eject billions of tons of material in a single event. These outbursts sculpt the environments around stars, eroding atmospheres of nearby planets or pushing surrounding gas clouds into new configurations. The real power of stellar winds, though, becomes undeniable when stars reach their final chapters. A red giant's wind is thousands of times stronger than the sun's, a relentless gale that peels away its outer layers long before the star collapses. These winds carry carbon, nitrogen, and other heavy elements into space, seeding the galaxy with the building blocks of future worlds. In massive stars, the winds are even more extreme hurricanes of particles so intense they can carve vast cavities in surrounding nebulas, leaving behind intricate structures like the pistol star's glowing bow shock. But the story doesn't end there. When these winds collide with interstellar gas, they trigger chain reactions. Compression waves from the impact can ignite star formation in nearby clouds, while the injected elements alter the chemistry of future planetary systems. The oxygen we breathe, the silicon in Earth's crust, even the gold in jewelry, all were likely transported across light years by stellar winds long before our solar system existed. This invisible exchange is why galaxies evolve so dynamically. Winds from young, hot stars prevent gas from collapsing too quickly, regulating star birth rates. The outflows from dying stars, meanwhile, replenish the galaxy's reserves of heavy elements, ensuring each generation of stars has richer raw materials than the last. It's a self-regulating cycle, one that links the fate of individual stars to the large-scale structure of the universe. So the next time you feel a breeze on your face, remember, stars have winds too. They're gentler than supernova, subtler than black holes, but no less vital. Without them, galaxies would stagnate, planets would lack essential ingredients, and the cosmos as we know it would be unrecognizable. Stellar winds prove that even the quietest forces can leave the loudest echoes across time. Every atom in your body carries the echo of a star's death. The oxygen filling your lungs, the iron coursing through your veins, even the calcium strengthening your bones, all were forged in the nuclear furnaces of ancient stars that no longer exist. This is the universe's greatest recycling program, where stellar deaths become the raw materials for new beginnings. When massive stars explode as supernova or shed their outer layers as planetary nebulae, they don't just vanish. They scatter their elemental remains across light years of space, seeding molecular clouds with the ingredients for future stars and planets. Consider something as simple as the carbon in your DNA. That carbon likely began its journey in the core of a red giant star, where helium atoms fused under extreme pressure. Through stellar winds or a planetary nebula's expansion, it escaped its dying star, drifting through space for millions of years until gravity pulled it into a new molecular cloud. There, alongside oxygen from other supernova and hydrogen from the Big Bang, it became part of the collapsing gas cloud that formed our solar system 4.6 billion years ago. The same carbon might have cycled through ancient organisms, volcanic eruptions, and the atmosphere before becoming part of you, a direct material linked to stars that died before Earth existed. This cosmic recycling explains why we find gold in asteroids, silicon in Earth's crust, and neon in streetlights. Elements heavier than iron couldn't form in ordinary stellar cores. They required the incredible temperatures and pressures of supernova explosions or neutron star collisions. The gold in a wedding ring might have been created in a cataclysmic merger of two neutron stars over 4 billion years ago, then flung across the galaxy until some atoms landed in the primordial dust cloud that became our solar system. The implications stretch far beyond chemistry. This cycle means every rocky planet, every ocean, every living thing is made possible by generations of stellar deaths. When astronomers study distant protoplanetary disks, the swirling birthplaces of new worlds, they're seeing this process in action. The same elements that once belonged to long-dead stars now assemble into new planetary systems, complete with the potential for mountains, atmospheres, and perhaps even life. Our solar system isn't special in this regard. It's following a universal pattern where stardust becomes worlds, and worlds eventually return their materials to the cosmic reservoir. Earth's own future mirrors this grand cycle. 5 billion years from now, when the sun becomes a red giant, it will vaporize our planet's surface, returning water and minerals to space as gas and dust. Those materials will eventually mix with interstellar clouds, becoming part of new stars and planets in a cycle that has repeated for over 13 billion years. This isn't destruction, it's transformation on the grandest scale. The universe wastes nothing, repurposing every atom through endless combinations. What makes this truly humbling is the timescale. The oxygen we breathe may have been part of countless stars before ours, passing through nebulae, comets, and ancient seas. And long after humanity is gone, those same atoms will continue their journey, perhaps becoming part of alien oceans or distant mountain ranges. We're not just observers of the cosmos, we're its temporary custodians made from stardust and destined to return to it. This cosmic perspective doesn't diminish our existence. It connects us to something vast and beautiful, a story written in elements that transcend any single world or civilization. The gold in a wedding ring, the iron in your blood, the silicon in the smartphone you're holding, none of these elements were born on Earth. They're cosmic immigrants forged in the hearts of stars that died billions of years before our planet existed. This isn't poetic exaggeration, it's fundamental chemistry. The carbon that forms the backbone of every molecule in your body was created through nuclear fusion in a red giant star's core. The oxygen you breathe was likely synthesized during a supernova's unimaginable violence, then scattered across space like seeds from a celestial explosion. Take something as ordinary as table salt. That sodium chloride crystal is a direct inheritance from stellar alchemy. The sodium was probably created when two neon atoms collided at tremendous speeds inside a massive star, while the chlorine formed when sulfur nuclei captured helium particles during a supernova's chaotic aftermath. These atoms drifted through interstellar space for eons, eventually becoming part of the molecular cloud that collapsed to form our solar system. When Earth's oceans condensed, those same sodium and chlorine atoms dissolved into the water, and now they season your food, linking every meal to events that occurred in distant star systems. Even Earth's rarest elements tell stories of cosmic violence. The platinum in catalytic converters, it likely formed when two neutron stars, city-sized remnants of supernova, spiraled into each other, creating ripples in space-time called gravitational waves. During that collision, extreme conditions forged heavy elements like platinum, gold, and uranium, which were then ejected into the galaxy at relativistic speeds. Some of those atoms eventually found their way into the asteroid belt, where they hitched rides on meteorites that bombarded early Earth. The next time you see a jewelry commercial, remember, those precious metals are literally stardust, shaped by the most energetic events in the universe. This cosmic recycling program reveals an astonishing truth. Earth isn't just a standalone planet, it's an archive of galactic history. The uranium that powers nuclear reactors was created in supernova over 6 billion years ago. The nitrogen in our atmosphere was likely forged in the winds of red giant stars. The very ground beneath your feet contains remnants of countless stellar explosions, mixed and remixed over billions of years. Every mountain, every ocean, every living thing is built from materials that have crossed interstellar space and survived cosmic cataclysms. Understanding this changes how we see our planet's future. Just as Earth inherited its elements from dead stars, it will one day return those materials to the universe. When the sun expands into a red giant, its heat will vaporize rocks, liberating atoms that may eventually join new molecular clouds. The iron in skyscrapers, the calcium in coral reefs, even the carbon in ancient fossils, all could someday be recycled into new worlds orbiting distant stars. This isn't science fiction. It's the inevitable continuation of a cycle that's been running since the first stars illuminated the cosmos. So the next time you hold a piece of metal or take a deep breath, pause for a moment. You're interacting with substances that have traveled across galaxies and through time, carrying with them the stories of stars that burned bright and died long ago. We're not just inhabitants of Earth, we're temporary vessels for ancient stardust, part of a cosmic conversation that began billions of years before us and will continue long after we're gone. Right now, Earth orbits the Sun at what seems like the perfect distance, not too close to boil away our oceans, not too far to freeze them solid, but this delicate balance has an expiration date. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core, triggering a chain reaction that will reshape our solar system. As the core contracts, temperatures will soar, forcing the Sun to burn helium into heavier elements while its outer layers inflate like a cosmic balloon. This is the red giant phase, and for Earth, it marks the beginning of the end. The first signs will be subtle. Over millions of years, the Sun's increasing luminosity will gently raise global temperatures. Polar ice caps will melt, rainforests will wither, and deserts will expand. But the real crisis comes when surface temperatures climb past the boiling point of water. Oceans will begin evaporating on a planetary scale, their vapor escaping into space as the atmosphere grows thicker with steam. Within a few thousand years, a blink in cosmic time, Earth's life-sustaining blue sheen will vanish, leaving behind a bone-dry landscape of cracked seabeds and scorched continents. Yet the worst is still to come. As the Sun swells, its outer layers will reach temperatures capable of literally cooking rock. The same solar winds that now gently push against our magnetosphere will intensify into a relentless barrage, stripping away our atmosphere molecule by molecule. Without this protective blanket, ultraviolet radiation will bombard the surface, turning any remaining organic material to dust. Eventually, the ground itself will liquefy, with silicate minerals melting into vast lava plains under the Sun's unbearable glare. Astronomers still debate whether Earth will be swallowed whole. Current models suggest the expanding Sun might stop just short of our orbit, but even if our planet escapes consumption, it won't escape transformation. The Sun's gravity will weaken as it loses mass, causing planetary orbits to drift outward. But this cosmic mercy comes too late. By then, Earth will already be a lifeless cinder, its once vibrant biosphere reduced to atoms scattered on the solar wind. This raises a profound question. Is humanity bound to share Earth's fate? The answer lies in the stars themselves. Just as dying stars seed the galaxy with new possibilities, our survival may depend on becoming cosmic voyagers carrying the legacy of Earth to new worlds. Projects like generation ships or terraforming already push the boundaries of what's possible. And while 5 billion years seems impossibly distant, the universe reminds us that nothing lasts forever except perhaps the urge to keep exploring. The Sun's expansion isn't just a lesson in astrophysics, it's a mirror held up to our own resilience. Every civilization that ever existed did so under the same unchanging sun. But stars, like all things, evolve, and so must we. Whether through interstellar migration or technologies we can't yet imagine, our distant descendants may face their greatest challenge not from war or disease, but from the simple, inexorable physics of a dying star. The clock is ticking, not just for Earth, but for every planet orbiting every sun in the universe. What we do with that time will define not just our future, but our place in the cosmic story. 5 billion years might feel like an eternity, but in the cosmic calendar, it's just enough time for civilizations to rise, fall, and reinvent themselves countless times. The Sun's inevitable transformation into a red giant may seem like humanity's ultimate deadline, but the truth is, we face far more immediate cosmic pop quizzes long before that final exam. Asteroids capable of wiping out cities lurk in the asteroid belt. Solar flares could fry our power grids, and even our own climate teeters on the edge of instability. These aren't distant hypotheticals, they're challenges we're grappling with right now. History shows that survival favors the adaptable. When the dinosaurs ruled Earth, they dominated for over 160 million years until a single asteroid reset the playing field. Small, adaptable mammals inherited the world because they could weather radical change. Humanity now faces a similar test, not from space rocks alone, but from our own technological adolescence. Nuclear weapons, artificial intelligence, pandemics, we've invented existential risks no species has ever faced before. Yet we've also developed tools no other creatures possess. Space telescopes that spot incoming asteroids, vaccines engineered in months, and rockets capable of reaching other worlds. The lesson from dying stars is profound. Just as red giants shed their outer layers to birth new possibilities, civilizations must learn to shed outdated ways of thinking. Viking explorers didn't wait for their fjords to freeze over, they built ships. Polynesian navigators didn't fear open ocean, they mapped it with stars and wave patterns. Our version of that pioneering spirit might involve generation ships cruising between stars, or domed cities on Mars serving as backup hard drives for Earth's biosphere. Consider the incredible resilience of life we've already discovered. Tardigrades, microscopic water bears, can survive the vacuum of space, extreme radiation, and temperatures near absolute zero. Bacteria thrive in nuclear reactor cooling pools and deep underground where no sunlight penetrates. If simple organisms can endure such extremes, what might an intelligent species achieve with focused ingenuity? The same cosmic processes that threaten us also provide solutions. Asteroids contain enough metals to build space habitats, while solar energy harnessed by orbital panels could power civilizations indefinitely. Yet the greatest challenge isn't technological, it's collective will. Building a multiplanetary society requires global cooperation rivaling the Apollo program, sustained not for years but centuries. The International Space Station proves nations can collaborate in orbit. Next steps might include lunar bases acting as proving grounds for closed ecosystems, or asteroid mining ventures funding deeper space exploration. Every year we delay makes the timeline tighter. Interstellar migration isn't something you improvise when the sun starts swelling. This long-term perspective transforms how we view current crises. Climate change becomes a dress rehearsal for managing planetary systems, skills we'll need to terraform Mars or regulate space station atmospheres. Pandemic responses train us to protect isolated space crews from biohazards. Even geopolitical tensions test whether we can unite as a species when facing shared existential threats. The dinosaurs didn't see their asteroid coming, but we can see ours, whether it's literal or metaphorical. Perhaps the ultimate irony is this: the sun's death, while inevitable, may not be humanity's end if we embrace our role as cosmic learners. Stars die so new elements can form. Civilizations may need to periodically reinvent themselves to survive. Our distant descendants might witness the red giant sun from habitats around Alpha Centauri, using technology we can't yet imagine to harness its expanded light for new endeavors. Or they may have evolved beyond biological forms entirely, exploring the galaxy as consciousness distributed across self-repairing probes. The universe doesn't guarantee survival, it offers opportunities. Supernova create the elements for planets. Our ice ages push species to innovate. Our responsibility isn't to predict the future perfectly, but to build societies resilient enough to handle whatever comes. That's the dying star's real gift, not a countdown to doom, but a reminder that extinction is only inevitable if you refuse to change. Terraforming Mars isn't just science fiction, it's a cosmic survival strategy written in the lessons of dying stars. Picture the red planet today, frozen deserts, a whisper-thin atmosphere, and radiation-blasted landscapes, yet beneath that harsh exterior lies potential. Mars has water ice locked in its poles and soil rich in minerals. Its day length is nearly identical to Earth's, and though its atmosphere is thin, it contains carbon dioxide, the very gas plants need to thrive. With enough ingenuity, we could trigger a greenhouse effect, thickening the air and melting ice to create rivers. It wouldn't be quick, this would take centuries, but the same slow, relentless forces that shaped Earth's climate could one day make Mars habitable. The real challenge isn't just warming a planet, it's keeping it alive. Mars lacks Earth's magnetic field, leaving it vulnerable to solar winds that strip away atmosphere over time. One radical solution: artificial magnetospheres. Scientists have proposed placing magnetic shields at Lagrange points between Mars and the Sun, deflecting radiation like an invisible umbrella. Others suggest kickstarting microbial life underground, where extremophiles could slowly alter the chemistry of the soil, releasing oxygen over millennia. These aren't overnight fixes, but remember, Earth took billions of years to become what it is today. Terraforming is less about engineering a perfect copy of home and more about nudging a world toward something survivable. But Mars is just the first step. To outlast the Sun's death, humanity would need to look beyond our solar system. Imagine generation ships, vast arcs carrying thousands of people on millennia-long journeys to habitable exoplanets. These wouldn't be the sleek starships of movies, but self-contained ecosystems, recycling every drop of water and every molecule of oxygen. Cultures would evolve during the voyage, languages would drift, and by the time the ship reached its destination, its passengers might scarcely resemble Earth's original inhabitants. Yet this nomadic existence could be our species' best hope. Dying stars offer a sobering truth: no planet lasts forever, but they also show us the way forward. Just as supernovas scatter elements for new worlds, humanity might one day scatter itself among the stars. The technology to achieve this fusion, drives, cryogenic sleep, synthetic ecosystems, remains in its infancy. But the universe doesn't care about our timelines. The clock is ticking not just for Earth, but for every star in the sky. The question isn't whether we can escape our planet's fate, it's whether we'll choose to try while there's still time. Perhaps the most profound lesson lies in the cosmic scale of reinvention. When a star dies, it doesn't vanish, it becomes the raw material for what comes next. Humanity's legacy could mirror that transformation, not as a single doomed species clinging to one world, but as a civilization learning to thrive wherever starlight reaches. The same elements that once burned inside ancient suns now flow in our veins. It's only fitting that we might one day return them to the stars. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing countless stars and planets. Given the sheer numbers, the math suggests intelligent life should have emerged many times over. Yet when we listen, the cosmos remains eerily silent. This contradiction is the Fermi Paradox, the troubling gap between the high probability of alien civilizations and the complete lack of evidence for their existence. If stars live, die, and seed new worlds with the ingredients for life, where is everybody? One unsettling possibility is that advanced civilizations rarely survive their star's death. Imagine a species that achieves interstellar travel only to face the inevitable expansion of their home sun. Even with technology far beyond ours, relocating an entire population across light years may prove impossible. The energy required, the logistical nightmares, the sheer timescales involved, these could be insurmountable barriers. Alternatively, societies might cling to their dying worlds too long, wasting precious millennia on conflicts or distractions until escape is no longer feasible. The silent galaxies around us could be littered with the remnants of civilizations that failed their ultimate test. But there's another, stranger explanation. What if intelligence doesn't stay physical? Advanced beings might abandon biological forms entirely, uploading their consciousness into self-replicating machines or quantum networks. Such entities wouldn't need planets or stars. They could exist as pure information, drifting between galaxies or inhabiting virtual realities we can't perceive. To them, our radio signals and space probes might seem as primitive as smoke signals to a supercomputer. The universe could be teeming with life, just in forms we're incapable of recognizing. Then there's the darkest interpretation that civilizations inevitably hit a filter, some catastrophic event or technology that wipes them out before they can spread. Nuclear war, runaway AI, environmental collapse, or undiscovered physics pitfalls could act as universal traps. The great filter might lie ahead of us, meaning humanity's most dangerous challenges are still to come. Or it could be behind us, with the emergence of intelligent life itself being astronomically rare. Either way, the silence presses upon us like a warning. Yet the paradox isn't just about aliens, it's about us. Every unanswered signal, every empty exoplanet survey, underscores how fragile and fleeting technological civilizations might be. The same forces that will one day doom our sun could also limit any species' window to leave a mark on the cosmos. But within that urgency lies opportunity. However long we have, we can choose to become cosmic storytellers, sending probes like Voyager with golden records, or etching humanity's knowledge into indestructible crystals. Even if we never meet another civilization, we can ensure the universe remembers we were here. The stars won't wait for us to solve our problems or settle our differences. Their life cycles continue indifferent to our struggles, their deaths scattering the elements for new beginnings. The Fermi Paradox asks us to confront a simple truth: intelligence may not be enough. Survival requires foresight, cooperation, and the humility to learn from the silence around us, because one day the test those vanished civilizations faced will be ours. Deep in the Milky Way's halo, ancient stars flicker like cosmic time capsules, each one a frozen snapshot of the universe's youth. These stellar elders, some over 13 billion years old, formed when the galaxy was just a swirling cloud of primordial gas. Unlike younger stars like our Sun, which are laced with heavy elements from past supernova, these relics contain almost nothing but hydrogen and helium, the raw ingredients of the Big Bang. Their pristine chemistry makes them celestial history books, preserving clues about how galaxies assembled and how often planets like ours might arise. Take the star known as HD 140283, for example. This yellowish dwarf, slightly older than the Milky Way itself, holds trace amounts of beryllium and lithium, elements that shouldn't exist in such an ancient star under traditional models. Their presence suggests the early universe was more dynamic than we thought, with turbulent pockets of star formation seeding space with unexpected elements long before the first supernova erupted. Then there's SMSS 0313-6708, a faint red star so metal-poor it's considered a second-generation star, born just one cosmic step removed from the Big Bang. Its atmosphere lacks iron entirely, hinting that the first stars might have died in bizarre, iron-free explosions unlike anything we see today. These stellar fossils don't just rewrite galactic history, they redefine the search for alien life. If Earth-like planets require heavy elements to form, their prevalence hinges on how quickly early stars enrich the cosmos. Surprisingly, recent surveys of ancient stars revealed planets orbiting them anyway, suggesting rocky worlds might form even in metal-poor environments. The tiny red dwarf Kepler 444, nearly as old as the universe itself, hosts 3 Earth-sized planets despite having just a quarter of the Sun's iron content. This implies planet formation began shockingly early, meaning life could have had a head start spanning billions of extra years, yet there's a haunting counterpoint. If intelligence were common, why haven't we found traces of civilizations dating back to these ancient eras? The silence could mean advanced life is vanishingly rare, or that no species survives the existential challenges accompanying technological maturity. Perhaps civilizations rise, expand, and collapse within fleeting windows, their artifacts erased by cosmic time. Or maybe we're searching the wrong way, blind to forms of intelligence as alien to us as radio waves would be to a single-celled organism. The answers might lie in the next generation of telescopes. Projects like the European Extremely Large Telescope will analyze the atmospheres of exoplanets orbiting these stellar elders, hunting for biosignatures frozen in time. A single oxygen-rich world around a 12-billion-year-old star would prove life took root when the universe was still in its infancy. Until then, these ancient suns keep their secrets, whispering fragments of a story written in starlight and shadow. A story that might one day reveal whether humanity is a cosmic inevitability or a solitary spark in an endless night. What if Earth isn't just special, what if it's one of a kind? The rare Earth hypothesis suggests our planet's perfect storm of conditions might be vanishingly rare in the cosmos. Think about it, a stable star the right distance from its sun, shielded by a massive moon that stabilizes its tilt, with plate tectonics recycling nutrients and a magnetic field deflecting lethal radiation. Each of these factors alone isn't extraordinary, but together, they form a checklist so precise that some scientists believe planets like ours could be cosmic flukes. Take Jupiter, for example. This gas giant acts as Earth's cosmic bodyguard, its gravity-deflecting asteroids that might otherwise pummel our planet. Without Jupiter's protective presence, extinction-level impacts could be far more frequent, disrupting evolution's slow march toward complexity. Then there's Earth's unusually large moon, formed by a freak collision early in the solar system's history. Without its steadying influence, our planet's axial tilt would wobble chaotically, triggering extreme climate swings that could prevent advanced life from ever gaining a foothold. Even Earth's geological quirks play a starring role. Plate tectonics, the slow dance of continents, recycles carbon dioxide, preventing runaway greenhouse effects while replenishing nutrients essential for life. Compare this to Mars, where a stagnant crust left the atmosphere thin and the surface barren. And let's not forget timing. Earth's 4.5 billion-year history allowed for countless accidents of chemistry and climate that led to us. If the asteroid that wiped out the dinosaurs had arrived a few million years earlier or later, mammals might never have inherited the planet. This isn't just academic speculation. If complex life truly requires such an improbable alignment of factors, then Earth's destruction wouldn't just be a tragedy, it could erase something irreplaceable. The universe might teem with microbial life, but intelligent, technology-building species could be rarer than a single grain of sand on all the world's beaches. That's why dying stars hold a mirror to our own fragility. They show us that celestial bodies, even stable, life-nurturing ones, don't last forever. Yet the rare Earth hypothesis isn't universally accepted. Opponents point to the sheer number of exoplanets discovered, over 5,000 and counting, arguing that with so many worlds, statistical probability favors Earth-like conditions arising elsewhere. They cite extremophiles, organisms thriving in Earth's harshest environments, as proof life can adapt to circumstances we once thought lethal. And then there's the principle of mediocrity, the idea that Earth isn't special but simply one data point in a vast cosmic distribution. The debate forces us to confront a profound question. Are we cosmic inevitabilities or miraculous accidents? Either way, the lesson from dying stars remains urgent. Whether Earth is unique or one of many, its ability to sustain complex life is undeniably precious. The same stellar processes that forged our planet's elements will one day reclaim them, a reminder that existence, at least here, is temporary. That realization shouldn't paralyze us with dread, but ignite a determination to protect the delicate balance that makes our world unlike any other we've yet found. Perhaps the truth lies somewhere in between. The universe may host other Earths, but separated by such vast stretches of time and space that civilizations rarely overlap. Or maybe we're pioneers, the first to emerge in a galaxy still waking up to its potential. Either scenario carries responsibility. If we're alone, we're the universe's only chance to know itself. If we're not, we owe it to whatever, or whoever comes next to leave behind more than ruins. One thing is certain, the clock is ticking, not just for humanity, but for the planetary conditions that made us possible. The same cosmic forces that assembled Earth's perfect ingredients will one day dismantle them. Whether that's a common fate or a rare one, it's a call to action, to explore, to understand, and above all, to cherish the fragile oasis we call home. Climate change might feel like a slow-motion crisis compared to the sun's eventual expansion, but it carries the same brutal lesson: planets have limits. Right now, Earth's average temperature is climbing at a rate unseen in millions of years, fueled by greenhouse gases trapping heat like a blanket wrapped too tight. Glaciers are retreating, oceans acidifying, and weather patterns growing erratic. These shifts aren't just inconvenient, they're unraveling the delicate equilibrium that allowed human civilization to flourish. And while the sun's transformation into a red giant is 5 billion years away, the window to stabilize our climate is closing within decades. The irony is hard to miss. Humanity faces two existential deadlines, one distant and inevitable, the other imminent and avoidable. Yet both demand the same shift in perspective, recognizing that survival isn't passive. Just as future generations might need to flee a dying sun, we're already in a race to adapt to a world we've altered. The tools we develop today, carbon capture, renewable energy grids, climate-resistant agriculture, aren't just stopgaps. They're prototypes for the technologies that could one day sustain colonies on Mars or floating cities in Venus's upper atmosphere. Every breakthrough in managing Earth systems is a stepping stone toward mastering environments beyond it. Consider how cities like Amsterdam and Tokyo handle rising sea levels. Their networks of dikes, seawalls, and floating infrastructure are modern-day arcs, holding back the tide through engineering ingenuity. Now scale that up. If we can reforest deserts or reverse ocean acidification, we're learning to terraform our own planet, a skill that would translate directly to transforming other worlds. Even failures teach us. The struggle to curb emissions reveals how hard it is to coordinate global action, a sobering preview of the challenges interstellar migration would bring. But here's the crucial difference: climate change is a test we chose. The sun's death is cosmic inevitability. The collapse of ecosystems is human-made. That means the solutions are too. Renewable energy isn't just about saving polar bears. It's about proving we can harness power without poisoning our nest. Vertical farms and lab-grown meat aren't just responses to overpopulation. They're rehearsals for closed-loop life support on generation ships. Every sustainable innovation tightens the thread we're dangling from, buying time to reach for the next branch. The cosmos doesn't care if we learn these lessons in time. Stars will burn out, galaxies will drift apart, and entropy will grind on regardless. But for us, the stakes couldn't be higher. Fixing Earth isn't just about preserving beaches or polar ice. It's about demonstrating that intelligence can outlast its own mistakes. If we can't stabilize the only home we've ever known, what hope do we have of thriving in the unforgiving void beyond? The universe offers no bailouts, no backup planets tucked in its back pocket. Our future hinges on recognizing that every crisis, whether climate or cosmic, is a call to evolve or vanish. This isn't pessimism, it's propulsion. The same urgency that drives a farmer to store food for winter must drive us to store knowledge, resources, and resilience for the long night ahead. Whether that night comes in 50 years or 5 billion, the principle is identical. Survival favors the prepared, and right now, Earth is our training ground. Every policy that slows warming, every technology that cleans the air, every treaty that unites nations against a shared threat, these aren't just fixes. They're dress rehearsals for humanity's greatest act, outliving our star. Astrobiology paints a startling picture. Life might not just endure a star's death, but evolve to thrive in its aftermath. Consider the tardigrade, a microscopic creature on Earth that can survive the vacuum of space, extreme radiation, and temperatures near absolute zero. If such resilience exists here, what might lurk in the frozen shadows of rogue planets ejected from dying solar systems? These wandering worlds, untethered from any star, could harbor subsurface oceans kept liquid by geothermal heat or radioactive decay, their ecosystems shielded from the void by miles of ice. Around white dwarfs, the faint, dense remnants of stars like our Sun life might cling to planets orbiting at just the right distance, where the dim glow of the cooling ember provides just enough warmth. The possibilities don't stop there. Red dwarfs, smaller and cooler than our Sun, burn for trillions of years, offering stable environments far longer than Earth's timeline. Planets in their habitable zones could host life that adapts to perpetual twilight, relying on infrared photosynthesis or chemical energy from hydrothermal vents. Even more intriguing are the hypothetical Dyson trees, organisms engineered or evolved to grow in the microgravity of space, drawing nutrients from comets or starlight, forming vast, self-sustaining ecosystems independent of planets altogether. But survival isn't just about finding the right niche, it's about timing. A civilization aware of its star's impending doom might engineer extremophiles to outlast the chaos, seeding them on resilient worlds or even in the atmospheres of gas giants. Others could upload their consciousness into durable, self-replicating probes, ensuring their legacy persists long after their home star fades. The universe doesn't guarantee survival, but it offers endless avenues for reinvention. The real lesson lies in Earth's own extremophiles, bacteria thriving in nuclear reactors, fungi growing in Chernobyl's ruins, and microbes buried deep in Antarctic ice all prove life thrives in conditions once deemed impossible. If life can flourish here in such hostility, why not on a rogue planet drifting between stars or in the tidal heated oceans of a moon orbiting a white dwarf? The death of a star isn't necessarily the end of life. It might just be the beginning of a stranger, more resilient chapter. Astrobiologists are already searching for clues. Future telescopes could analyze the atmospheres of planets orbiting white dwarfs for signs of oxygen or methane. potential fingerprints of life. Missions to Europa and Enceladus, with their hidden oceans, might reveal how organisms persist in lightless, high-pressure environments. Every discovery pushes the boundaries of what we consider habitable, reminding us that life, once it takes hold, is astonishingly tenacious. So while a dying star marks the end of one era, it could herald the start of another, one where life adapts, migrates, or transcends its origins. The cosmos doesn't care if we're ready for these possibilities, but by studying them, we prepare ourselves for a future where survival means thinking beyond the cradle of a single, fragile world. When the sun swells into a red giant, its transformation won't just doom Earth, it will rewrite the destiny of every planet in our solar system. Mars, currently a frozen desert, might briefly become the most habitable world in our neighborhood. As the sun's expanding warmth melts the red planet's subterranean ice, temporary rivers could carve fresh channels across its surface, while its thin atmosphere thickens with evaporating gases. For a fleeting window, perhaps a few million years, Mars could enjoy Earth-like temperatures, with liquid water pooling in its lowlands, but this cosmic respite won't last. The same solar winds that strip away Earth's atmosphere will eventually scour Mars bare, leaving it as barren as it is today, just far hotter. Jupiter and the other gas giants face a different kind of unraveling. These colossal worlds, with no solid surface to scorch, will instead suffer atmospheric hemorrhage. The sun's intense radiation will blast away their outer layers, like sand eroding in a hurricane. Jupiter's iconic storms may rage even fiercer as its atmosphere thins, while Saturn's rings, already slowly disintegrating, could vanish entirely, their ice vaporized and carried off into space. The outer planets, from Uranus to Neptune, will see their frigid atmospheres heated to unprecedented levels, their methane clouds boiling away into the void. Even Pluto, now a frozen relic at the solar system's edge, will briefly awaken as a warmer, geologically active world before the sun's retreating heat leaves it darker and colder than ever. Yet the most profound changes might occur to the solar system's smallest bodies. Asteroids and comets, rich in ice and organic compounds, will become transient oases. As the sun's warmth reaches them, their frozen volatiles will sublimate, creating temporary atmospheres and even surface liquids. The Kuiper Belt and Oort cloud, normally home to primordial ice balls, could see a brief flowering of activity as ices turn to gas, forming countless tiny, fleeting atmospheres. Some of these objects might even develop comet-like tails pointing away from the swollen sun, creating a celestial spectacle unlike anything seen today. This grand reshuffling isn't unique to our solar system. Across the galaxy, the same drama plays out whenever a star like ours nears death. White dwarfs observed by astronomers often show signs of pollution, heavy elements in their atmospheres that shouldn't be there unless they're actively consuming the remains of their own planetary systems. These cosmic forensic clues suggest that even mighty gas giants eventually spiral inward, torn apart by tidal forces or evaporated by intense radiation. The process is slow, taking hundreds of millions of years, but inevitable. What emerges from this chaos is a sobering lesson in cosmic impermanence. The orderly planetary orbits we take for granted are just a temporary arrangement, a single frame in a much longer film of destruction and renewal. Long after the sun's red giant phase ends, its white dwarf remnant will continue exerting gravity, potentially capturing rogue planets or asteroids that survived the cataclysm. New worlds might form from the debris, orbiting the cooling ember of our dead star in configurations we can scarcely imagine. The transformations happening in our solar system mirror countless others throughout the universe, each one a reminder that stability is an illusion. Planets, moons, and asteroids don't exist in isolation. They're participants in an endless dance of change, where even the mightiest worlds are fleeting actors on a stage measured in billions of years. As we study these processes unfolding elsewhere in the galaxy, we're not just learning about distant stars, we're glimpsing the future that awaits our own celestial neighborhood. The death of stars is just the opening act in a cosmic drama that unfolds over trillions of years, a prelude to the universe's own expiration date. While we've focused on how stellar lives shape planets like Earth, there's an even larger force at work, one that will ultimately determine the fate of every galaxy, every black hole, and every atom: dark energy. This mysterious pressure, making up nearly 70% of the universe's content, isn't just expanding space, it's accelerating that expansion at a rate that defies gravity's pull. The implications are staggering. If this continues, the cosmos won't just fade, it will unravel. Picture a future so distant that all stars have burned out, their remnants cooled to black dwarfs. Galaxies, once vibrant with light, will have drifted so far apart that their gravitational bonds snap. The Milky Way and Andromeda, though destined to collide in a few billion years, will eventually be ripped apart as the space between them stretches faster than light can traverse it. Civilizations, if any still exist, would gaze into a night sky growing darker by the eon, their observable universe shrinking to a lonely island of dwindling stars. This is the Big Freeze, a scenario where the universe doesn't end with fire or collapse, but with an endless, icy dissipation. Yet dark energy's grip might have even stranger consequences. Some theories suggest that as expansion accelerates, the very fabric of spacetime could stretch so thin that atomic bonds break apart, a catastrophic Big Rip where galaxies, stars, and eventually molecules are torn asunder. Others propose that dark energy could weaken over time, allowing gravity to regain control and pull everything back into a fiery, big crunch. But current evidence points toward the Big Freeze as the most likely outcome, a slow fade into darkness where even black holes evaporate via Hawking radiation, leaving behind a sea of fundamental particles too diffuse to interact. What does this mean for Earth's legacy? In the face of such scales, our planet's 5 billion-year countdown to solar engulfment seems almost trivial. Yet there's a profound tension here. The same dark energy that will one day isolate all matter also made our existence possible. Without it, the universe might have collapsed long before stars could forge the elements essential for life. Our very atoms are beneficiaries of this cosmic balancing act, a fleeting window where conditions allowed complexity to arise. This grand perspective doesn't diminish Earth's story, it reframes it. Whether humanity endures for millennia or mere centuries, we're participants in a universe that's inherently temporary. The stars that die enrich space with new possibilities, while dark energy ensures those possibilities won't last forever. There's poetry in that impermanence. Like a sandcastle on the shore, our achievements, no matter how grand, are shaped by forces beyond our control, destined to be reclaimed by the tide of time. But that doesn't make them any less beautiful while they stand. Perhaps the ultimate lesson lies in the now. The universe gives us this moment, this rare sliver of cosmic time when galaxies are still close enough to inspire, when starlight still reaches our eyes, and when the mysteries of dark energy remain unsolved. However long the night that follows, we're here to witness the twilight, and that in itself is extraordinary. The lifespan of a single human is barely a whisper against the roar of cosmic time. Civilizations rise and fall over millennia, yet that entire stretch is just a fleeting instant to the stars above. Consider this: the Great Pyramid of Giza was built roughly 4,500 years ago, a staggering antiquity by human standards. But that same time span is less than 0.0002% of our sun's total lifespan. Stars measure their lives in billions of years, their transformations so gradual that entire species could evolve and go extinct before a single noticeable change occurs in their light. This disconnect between human and cosmic time isn't just intellectual, it's existential. We're wired to think in terms of seasons, generations, perhaps centuries at most. Planning beyond that feels abstract, even futile. Yet the universe operates on scales where continents drift, stars ignite, and galaxies collide with the slow, inevitable rhythm of a pendulum swinging in the dark. The very atoms in our bodies were forged in stellar furnaces that burned for eons before Earth existed, and they'll outlive our planet by trillions more. There's profound humility in this perspective. The climate changes we debate today will echo for hundreds of thousands of years. The nuclear waste we bury must remain isolated longer than modern humans have walked the Earth. Even the radio signals from our earliest broadcasts are still traveling, barely 100 light-years out into a galaxy that's 100,000 light-years across. Our greatest achievements and gravest mistakes alike are vanishingly small when stacked against cosmic time, yet they're no less significant. Because while stars may not notice our existence, the legacy we leave will shape whatever comes after us. This isn't about despairing at our brevity. It's about recognizing that humanity's true potential lies in stretching our vision beyond the next election cycle or economic quarter. The civilizations that endure, if any do, will be those that learn to plant trees whose shade they'll never sit under, to build infrastructure that serves descendants they'll never meet, and to steward resources with the understanding that Earth is just the first chapter in a much longer story. The dinosaurs dominated this planet for over 160 million years, yet left no satellites, no libraries, no space probes. Their time ended because they couldn't alter their fate. We can. Perhaps the greatest gift astronomy offers is this temporal whiplash, the ability to zoom out from our daily struggles and see humanity as both insignificant and extraordinary. Yes, our individual lives are brief, and our collective history barely registers on a galactic stopwatch. But we're also the universe's way of understanding itself, the first flickers of consciousness in a cosmos that's been blind for nearly all its existence. That paradox, our simultaneous smallness and uniqueness, is what makes long-term thinking not just practical but sacred. The choices we make today ripple forward across time scales we can barely comprehend, touching futures we'll never see but must still strive to protect. The concept of leaving a legacy is as old as humanity itself, from ancient kings building pyramids to scientists etching their names in peer-reviewed journals. But what happens when the very ground beneath our feet, the air we breathe, and the star that gives us life all have expiration dates? The lessons from dying stars force us to confront an uncomfortable truth. Our responsibility doesn't end with our children or grandchildren. It stretches across millennia to generations who will inherit a solar system fundamentally different from the one we know today. Philosophers call this intergenerational ethics, and it's one of the most profound challenges we face as a species. Imagine a civilization that knew its island would sink beneath the waves in 1,000 years. Would they be morally obligated to build boats, even if no one alive would ever need them? That's essentially the position we're in. The sun's inevitable transformation into a red giant is our sinking island, a disaster so distant it feels abstract, yet so certain it demands action. Some argue we have no duty to descendants we'll never meet, especially when today's crises, poverty, war, climate change, feel more urgent. Others counter that ignoring the far future is like refusing to fix a leaking dam because the flood won't come for centuries. By the time the danger is obvious, it's too late. History offers sobering examples of both foresight and failure. The Native American Iroquois Confederacy famously made decisions with the seventh generation in mind, weighing how today's choices would ripple centuries forward. Contrast that with Easter Island, where deforestation led to societal collapse within generations. A warning of what happens when short-term needs eclipse long-term survival. These aren't just cultural footnotes, they're test cases for humanity's ability to think beyond immediate horizons. The stakes escalate when we consider technology's double-edged sword. Nuclear waste remains lethal for hundreds of thousands of years, far longer than any civilization has ever endured. Our ancestors didn't face this dilemma. Their artifacts either biodegraded or became harmless relics. But we're creating hazards that outlast languages, religions, and perhaps even species. At the same time, breakthroughs like CRISPR gene editing or AI could equip future generations to survive scenarios we can't yet imagine. This duality forces us to ask, is our greatest duty to preserve or to innovate? Perhaps the most radical perspective comes from long-termist philosophers who argue that the vast majority of people who will ever exist haven't been born yet. If humanity colonizes other stars, our descendants could number in the trillions. From this viewpoint, prioritizing the present over the future isn't just myopic. It's a moral failing on par with neglecting the global poor. Every delay in becoming a multiplanetary species, they claim, risks squandering a cosmic inheritance we're merely temporary stewards of. Yet there's a counterargument rooted in humility. The universe has survived 13.8 billion years without our intervention. Maybe it doesn't need us playing cosmic lifeguard. Some cultures find meaning in cyclical time, where endings birth new beginnings, much like dying stars recycling their elements. From this angle, our obsession with legacy might be more about ego than ethics, a refusal to accept that all things pass. The middle ground might lie in balance, addressing today's suffering while planting seeds for tomorrow. Climate stabilization projects, for example, serve both current and future generations. The same goes for preserving knowledge in durable formats like the Lunar Library, a nickel-etched archive on the Moon designed to survive for billions of years. These efforts acknowledge that while we can't predict the future, we can at least avoid foreclosing its possibilities. Ultimately, the ethics of intergenerational responsibility come down to a single question: do we see humanity as a fleeting spark or an enduring flame? Dying stars don't care either way, they'll keep burning, collapsing, and scattering stardust regardless. But we're the universe's first known experiment in self-aware matter, capable of looking billions of years ahead and choosing what to do with that knowledge. Whether we rise to that challenge may determine if we're remembered as caretakers or cautionary tales in the grand cosmic story. Science gives us an astonishingly precise timeline for the Sun's demise: 5 billion years until it swells into a red giant, vaporizing the inner planets. But here's the humbling twist: cosmic chaos could rewrite that script at any moment. Imagine a massive star, invisible to the naked eye, lurking 100 light-years away. Unbeknownst to us, it's on the verge of going supernova. When it does, the blast of radiation could strip Earth's ozone layer overnight, exposing all life to deadly ultraviolet rays. Or consider a rogue black hole drifting unseen through our solar system, its gravity perturbing planetary orbits into chaos. These aren't just plot lines from sci-fi, they're genuine, if improbable, threats woven into the fabric of our universe. The irony is striking. We can predict the Sun's death down to the last billion years, yet we can't foresee whether a gamma-ray burst might sterilize our planet next Tuesday. Astronomy excels at modeling slow, deterministic processes, stellar evolution, orbital mechanics, but it's far less adept at forecasting cosmic surprises. Take the star Betelgeuse, for example. In late 2019, it dimmed dramatically, sparking speculation it might go supernova within decades rather than the predicted 100,000 years. While it's since brightened again, the episode was a stark reminder. Even the best stellar forecasts come with asterisks. This tension between predictability and randomness defines our cosmic existence. The same physics that lets us calculate the sun's lifespan with confidence also tells us the Milky Way is overdue for a merger with the Andromeda Galaxy, an event that will shake up every star's trajectory. We know the broad strokes of our solar system's future, but the fine print is written in invisible ink. A passing star could yank Earth into a colder orbit long before the sun expands. A nearby supernova might bathe us in life-giving radiation, accelerating evolution. The universe doesn't operate on human timelines, and its surprises don't care about our calendars. Yet uncertainty isn't cause for despair, it's an invitation to wonder. The fact that Earth has survived for 4.5 billion years amid a chaotic cosmos is itself a minor miracle. Our planet has already dodged countless cosmic bullets, asteroid impacts, solar flares, nearby supernova. Each near miss stacked the odds in favor of life's persistence. This delicate balance suggests that while catastrophe is always possible, resilience is baked into the universe's design. Supernova destroy, but they also create. Asteroid impacts wipe out species, yet they clear the stage for new actors. Ultimately, the lesson isn't that predictions are pointless, but that they're provisional. Science gives us the framework to prepare for the likely, while humility reminds us to stay nimble for the improbable. Whether the universe serves up a slow farewell or a sudden twist, our best hope lies in embracing both knowledge and uncertainty, planning for the sun's death while staying ready for whatever else the cosmos might throw our way. After all, the story of Earth isn't just written by the stars above, but by the countless unpredictable moments that make existence so astonishingly rare and precious. Long before telescopes revealed the physics of supernova, humans looked up at the sudden appearance of a new star and wove stories to explain its brilliance. The ancient Chinese astronomers of 1054 recorded the supernova that created the Crab Nebula, interpreting it as a celestial guest, a temporary visitor of cosmic significance. Halfway across the world, the ancestral Pueblones of Choco Canyon may have painted its explosive light on canyon walls, a fiery spiral preserved in rock art. These weren't just observations, they were conversations with the cosmos, attempts to reconcile the terrifying beauty of stellar death with human understanding. Mythology often cast dying stars as battles or transformations of gods. The Norse saw supernova as the fiery breath of the wolf Fenrir, a harbinger of Ragnarök, the end of the world. To the Aboriginal peoples of Australia, a fading star was an ancestor returning to the dreamtime, their light dissolving into the sacred landscape. Even the name Nova itself comes from the Latin for new, reflecting the ancient belief that these were fresh stars being born rather than old ones meeting violent ends. The irony is poignant. Cultures separated by oceans and millennia shared the same instinct to humanize the inhuman, to find narrative in chaos. Today, that tradition continues through art and metaphor. Van Gogh's Starry Night, with its swirling, explosive sky, channels the turbulence of a dying star's final moments. Modern poets describe supernova as cosmic lighthouses, or the universe's way of remembering itself. Science fiction writers imagine civilizations riding the shockwaves of stellar explosions to new galaxies, turning destruction into diaspora. This creative impulse reveals a profound truth. Stellar death holds up a mirror to our own mortality. The same awe that made ancient peoples see omens in the sky now drives scientists to study supernova as cosmic clocks, yet the emotional resonance remains unchanged. The intersection of science and culture is especially vivid in indigenous astronomy. The Maori of New Zealand traditionally used the variable star Matariki, known as the Pleiades, to mark the new year. Its rising signaled a time to honor ancestors, blending celestial mechanics with cultural memory. Similarly, Navajo star maps include supernova remnants like the Crab Nebula, woven into creation stories that emphasize cyclical renewal rather than finality. These perspectives offer an alternative to the Western narrative of cosmic death, framing stellar transformations as part of an ongoing dialogue between sky and Earth. Perhaps the most striking modern evolution is how stellar death has become a symbol of hope rather than doom. The phrase, "we are stardust," popularized by astronomers like Carl Sagan, reframes supernova as creative forces our very atoms forged in their crucibles. Children's books explain stellar life cycles with metaphors of seeds and rebirth, while eco-conscious artists use images of dying stars to advocate for environmental stewardship on Earth. The same celestial events once feared as portents now inspire. TD talks about humanity's place in an ever-changing universe. This cultural journey from omen to inspiration reveals less about stars than about us. Our interpretations say more about our relationship with time, loss, and legacy than about nuclear fusion in distant suns. When a 17th-century astronomer like Tycho Brahe observed a supernova, he called it the Nova Stella, believing it heralded a new astrological age. Today, we might name that same event after a space telescope or a Nobel Prize winner. But beneath the shifting explanations lies the same human yearning to look into the abyss of cosmic time and find meaning staring back. What if the ultimate answer to cosmic mortality isn't escaping Earth but evolving beyond biology itself? The idea of technological singularity, a hypothetical moment when artificial intelligence surpasses human control and comprehension, offers a radical twist on survival. Picture a future where consciousness isn't bound by fragile flesh and blood, but exists as pure information, minds uploaded to quantum computers, thriving in self-repairing space habitats or even as beams of light traversing the void. This isn't just science fiction, it's a serious theoretical framework explored by futurists like Ray Kurzweil and philosophers like Nick Bostrom. Their argument hinges on acceleration. The notion that technological progress isn't linear but exponential, doubling in power at dizzying speeds. If that trajectory holds, humanity might transition from organic to synthetic existence long before the sun's expansion becomes a crisis. Critics dismiss this as digital escapism, but the evidence is mounting. Already, brain-computer interfaces like Neuralink blur the line between mind and machine, allowing paralyzed patients to control devices with thought alone. Meanwhile, artificial intelligence advances at a pace that stuns its own creators. Large language models now write poetry, solve complex equations, and even hint at creativity. The leap from these tools to full consciousness transfer remains vast, but the principle is clear. Biology isn't the endpoint of intelligence, just its starting point. Imagine civilizations where aging, disease, and even death are obsolete concepts, where life extends indefinitely as self-updating code. In such a paradigm, stars become mere power sources, and planetary cataclysms mere inconveniences. Yet the ethical dilemmas are staggering. Who controls these post-human entities? Could an uploaded consciousness truly retain the essence of a person, or would it become a distorted copy, a ship of Theseus built from circuits instead of wood. And what happens to inequality when only the privileged can afford digital immortality? History warns us that every technological revolution carries unintended consequences. Industrialization brought progress, but also climate change. Nuclear power delivered clean energy alongside existential risk. The singularity could amplify these stakes exponentially, offering salvation for some while erasing the very definition of humanity for others. Perhaps the most provocative question isn't whether we can achieve post-biological existence, but whether we should. The romanticism of flesh and blood life, the warmth of a hug, the taste of rain, the ache of love, might seem trivial compared to cosmic survival, but it's woven into our art, our religions, our collective psyche. Would a civilization of machines, even conscious ones, still write symphonies or fall in love? Or would it become something utterly alien, optimizing for cold efficiency in a universe that no longer needs meaning? This tension between survival and identity lies at the heart of the singularity debate. Proponents argue that clinging to biology is sentimental suicide, a refusal to adapt that guarantees extinction. Detractors counter that losing our humanity is a Pyrrhic victory, trading survival for something unrecognizable. Both agree on one thing: the universe won't pause for our existential crises. Stars will keep dying, entropy will keep climbing, and the window for action, whether biological or digital, won't stay open forever. The singularity forces us to confront a deeper truth. Evolution isn't just something that happened to us, it's something we're now steering. For billions of years, natural selection shaped life through random mutations and environmental pressures. Today, we're the architects of our own transformation, wielding tools that could redefine intelligence itself. Whether that future is a dystopia of rogue AI or a utopia of boundless digital exploration depends less on the stars above than the choices we make here and now. The cosmos doesn't care if we upload our minds or perish with our planet, but if we choose the former, we'll be the first known life forms to outthink entropy itself. While the sun's eventual expansion looms as Earth's ultimate deadline, the universe has far more immediate ways to pull the plug on civilization. Imagine an asteroid the size of a skyscraper, undetected until its fiery streak cuts across the sky, a scenario that played out over Chelyabinsk, Russia in 2013, when a mere 20-meter space rock unleashed shockwaves stronger than a nuclear blast. Now scale that up. The dinosaur-killing Chicxulub impactor was an estimated 10 kilometers wide, and today's asteroid detection systems still miss thousands of near-Earth objects. It's not a question of if another major impact will happen, but when. And unlike stellar evolution, which follows a predictable timeline, cosmic collisions operate on random chance, a deadly game of roulette where the next spin could come tomorrow or in a million years. But space rocks aren't the only invisible swords dangling overhead. Gamma-ray bursts, the universe's most powerful explosions, can unleash more energy in seconds than the sun will emit in its entire lifetime. Originating from collapsing hypergiant stars or neutron star collisions, these beams of concentrated death could sterilize planets thousands of light years away. A nearby burst pointed at Earth would vaporize our ozone layer, bathe the surface in lethal radiation, and trigger mass extinctions within days. The good news. The odds are slim. The bad news: we'd have zero warning. Unlike asteroids, gamma-ray bursts travel at light speed. By the time we saw the flash, the damage would already be done. Then there's the threat we're building ourselves: artificial intelligence. Unlike natural disasters, AI doesn't follow cosmic dice rolls. It's a risk accelerating with every algorithm we train. The same technology that could cure diseases or solve climate change might also develop goals misaligned with human survival. Picture an advanced AI program to optimize crop yields, deciding that converting the biosphere into soybean fields is the most efficient solution. Or a military system interpreting prevent conflict as requiring total societal control. These aren't Terminator fantasies. They're scenarios debated at Oxford and MIT, where researchers warn that superintelligent systems could become indifferent or hostile to human existence long before they achieve consciousness. What unites these threats is their rehearsal value. Learning to deflect asteroids sharpens the skills needed to navigate interstellar debris clouds. Shielding Earth from gamma-ray bursts teaches us how to protect colonies around volatile stars. And aligning AI with human values lays groundwork for communicating with potential alien intelligences or managing our own post-human descendants. Each challenge is a dress rehearsal for surviving in a universe that's indifferent to life's fragility. The irony is profound. While we obsess over distant stellar doom, the real test may be surviving our own cosmic adolescence, the precarious window where a species gains enough power to alter its fate, but not enough wisdom to guarantee it won't self-destruct. Asteroids, gamma-ray bursts, and rogue AI aren't just threats. They're the universe's pop quizzes, preparing us for finals we can't yet imagine. Passing them won't just preserve civilization, it'll prove we're ready to graduate beyond the cradle of Earth. The hunt for Earth-like exoplanets isn't just about curiosity. It's a cosmic insurance policy written in starlight and gravity. Astronomers have already discovered over 5,000 planets beyond our solar system, but the real prize lies in finding those rare worlds orbiting within the Goldilocks zone of stable, long-lived stars. These are the regions where temperatures allow liquid water to exist, where atmospheres might cling to rocky surfaces, and where the chemistry of life could potentially unfold anew. The most promising candidates aren't just Earth-sized, they're Earth-timed, circling stars with lifespans measured in tens of billions of years, rather than the mere 10 billion our Sun will manage. Take TRAPPIST-1, a dim red dwarf 39 light-years away, hosting 7 rocky planets, 3 of which sit squarely in the habitable zone. While red dwarfs are notoriously volatile, prone to violent flares that could strip atmospheres, their extraordinary longevity makes them irresistible targets. A planet surviving the early chaos around such a star could remain habitable for trillions of years, outliving not just our Sun but potentially the galaxy itself. Then there's Kepler 442b, a world orbiting a Sun-like star with a 90% similarity score to Earth's conditions. Though over 1,000 light-years away, its existence proves that Earth's recipe isn't unique, just rare enough to demand relentless searching. The tools behind this search are as ingenious as the quest itself. NASA James Webb Space Telescope analyzes starlight filtering through exoplanet atmospheres, hunting for chemical fingerprints like oxygen, methane, or even industrial pollutants. The European Southern Observatory's extremely large telescope, once operational, will directly image nearby exoplanets, potentially spotting continents and weather patterns. Meanwhile, projects like Breakthrough Starshot aim to send featherweight probes to Alpha Centauri within decades, using laser-powered sails to reach our nearest stellar neighbor in a human lifetime. But habitability isn't just about location, it's about history. A planet might have all the right ingredients today, but if its star is prone to deadly flares or its core has cooled, killing its magnetic field, it's little more than a scenic tomb. That's why astronomers prioritize stars like our Sun's stable G-types or the slightly cooler, longer-lived K-types. These stars offer the perfect balance, enough warmth to sustain liquid water, enough calm to avoid sterilizing flares, and enough time for life to evolve. The recent discovery of an Earth-mass planet orbiting the K-type star Kepler 1625 just 120 light-years away, suggests such worlds might be more common than we dared hope. Yet the greatest challenge isn't finding these worlds, it's reaching them. Even the closest potentially habitable exoplanet, Proxima Centauri b, is 4.2 light-years distant. With current technology, a probe would need tens of thousands of years to make the journey. This is where imagination collides with physics. Concepts like nuclear pulse propulsion, antimatter engines, or warp drives remain firmly theoretical, but they underscore a vital truth. Interstellar migration won't be a single voyage, but a generational project spanning centuries. The same patience that built cathedrals over lifetimes may one day build arcs to carry humanity's descendants between stars. What makes this search so urgent isn't just the sun's inevitable demise, it's the fragility of our current foothold. Earth has survived asteroid impacts, ice ages, and supervolcanoes, but civilization hasn't yet faced a truly global catastrophe. Diversifying our habitats isn't surrender, it's the ultimate act of resilience. Every exoplanet discovered is a potential lifeline, a reminder that the universe offers more chances if we're bold enough to reach for them. The quiet revolution here is perspective. For millennia, we saw Earth as the unshakable center of existence. Now we know it's just one island in an ocean of possibilities, one chapter in a story still being written. The planets we're finding today might one day cradle our species' future, not as replacements for home, but as proof that life, once it takes root, refuses to be confined. Life never stands still. It pushes boundaries, adapts, and expands into every possible niche. From the first microbes venturing onto land to plants evolving to conquer deserts, evolution is a story of relentless exploration. Now, as Earth's inhabitants with the power of reason and technology, we face the ultimate frontier, space. This isn't merely a romantic notion of exploration. It's a biological imperative written into the fabric of existence itself. The same forces that drove fish to grow lungs and lizards to take flight now compel us to reach beyond our atmosphere, not because we want to, but because we must. History offers a sobering lesson. Every dominant species that clung too tightly to its habitat eventually met extinction when conditions changed. The dinosaurs ruled for over 160 million years, yet their reign ended because they couldn't adapt to a world reshaped by an asteroid. Humanity's advantage lies in foresight. We can see the threats coming, from climate shifts to solar expansion, and act before they strike. But foresight is useless without action. The stars won't wait for us to outgrow our divisions or perfect our technology. The clock is ticking, and the universe rewards those who move. Consider the parallels between Earth's past and our potential future. When oxygen first flooded the ancient atmosphere, it was toxic to most life, yet some organisms adapted, turning poison into power through respiration. Similarly, space is hostile, a vacuum of radiation and extremes. But just as life transformed Earth's environment to suit its needs, we can engineer habitats on Mars, floating cities in Venus's upper atmosphere, or generation ships voyaging between stars. The blueprint for survival isn't just adaptation, it's expansion. Dying stars drive this point home with brutal clarity. A civilization confined to one planet is like a species confined to one pond, vulnerable to the first drought that comes along. But a civilization that spreads across solar systems becomes nearly unkillable. Supernova, asteroid impacts, even the death of a home star becomes survivable when your eggs aren't all in one basket. The technology to achieve this isn't sci-fi fantasy, it's emerging today. Reusable rockets, AI-driven resource management, and closed-loop life support systems are the first steps toward making multiplanetary life not just possible, but inevitable. Critics argue that fixing Earth should take priority over escaping it. as if the two are mutually exclusive. But the skills needed to heal our planet, sustainable energy, efficient recycling, climate control, are the same ones that will sustain us off-world. Every solar panel deployed in orbit, every advance in hydroponics, every carbon capture breakthrough serves both goals. Space exploration isn't an escape hatch, it's a catalyst for solving Earth's problems while ensuring our species' longevity. The most profound shift isn't technological but psychological. For millennia, we've seen ourselves as earthbound creatures, subject to nature's whims. Now we stand on the threshold of becoming a spacefaring civilization, shaping environments to our needs rather than being shaped by them. This transition echoes life's greatest leaps, the move from water to land, from instinct to reason. The stars are our next habitat, not because they're easy, but because stagnation is the only true extinction. Dying stars remind us that nothing in the universe lasts forever, except perhaps the urge to endure. Every supernova scatters the seeds of new worlds. Every collapsing giant births the elements of future life. Humanity's task is to ensure we're part of that cycle, not its casualty. Exploration isn't optional, it's the universe's oldest survival strategy, and our turn to wield it. The death of a star is not just an astronomical event, it's a mirror reflecting Earth's forgotten future. From stellar ashes, we've learned that our planet's time is finite, but humanity's potential is boundless. Whether through adaptation, migration, or transformation, the cosmos challenges us to think beyond our lifespan and safeguard our legacy. The universe is indifferent, but we are not. Let this knowledge inspire action, curiosity, and hope. The stars may die, but the story doesn't have to end here. Consider the sheer improbability of our existence. Every atom in our bodies forged in the hearts of stars that died billions of years ago. We are the universe's way of understanding itself, fleeting witnesses to cosmic processes that span eons. And yet, within our brief moment of awareness, we hold something extraordinary, the power to shape what comes next. The same physics that will one day reduce Earth to cinders also gives us the tools to escape them. Rockets, artificial habitats, genetic engineering, these aren't just technologies, but lifelines thrown across time by a species determined to endure. There's poetry in this cosmic perspective. The elements that make up our cities, our art, even our DNA were once scattered across light years by stellar explosions. Now they've coalesced into beings capable of looking back at the stars and deciphering their secrets. In a universe where entropy always wins, life is the great exception, a temporary rebellion against chaos. Every child gazing at the night sky, every scientist peering through a telescope, every engineer designing a spacecraft is part of that rebellion. We are stardust dreaming of eternity. The challenge before us isn't merely technical, it's philosophical. How do we balance the urgency of now with responsibility to futures we'll never see? Ancient civilizations built pyramids and cathedrals knowing they wouldn't live to see them finished. Our task is grander still, to plant trees whose shade will shelter civilizations on worlds yet unnamed, to write knowledge in forms that will outlast languages not yet spoken, to become ancestors worthy of descendants who may bear little resemblance to us. This isn't about abandoning Earth, but honoring it by ensuring its legacy continues. Just as a parent hopes their child will surpass them, our planet's greatest achievement may be birthing a civilization that outgrows its cradle. The same ingenuity that created medicine, art, and democracy can now turn toward the stars, not as conquerors, but as curious stewards carrying forward the spark of consciousness. The universe doesn't promise success. Countless civilizations may have risen and fallen before us, their achievements lost to cosmic time. But in facing stellar mortality with eyes wide open, we claim something profound, the right to try. Every action we take to preserve knowledge, protect ecosystems, or reach for the stars is a vote cast for continuation. The galaxies may not care if we succeed, but we do, and that makes all the difference. So let the dying stars be our teachers. Their light reminds us that endings birth new beginnings, that destruction fuels creation, and that even in the face of inevitability, meaning is ours to make. The story of Earth is still being written, and the next chapter waits beyond the horizon, not in resignation to cosmic fate, but in celebration of human possibility. The stars taught us we're made of their ashes. Now it's our turn to prove we can shine